Okay, our final example today, example 7. The distance necessary to stop a subway train at a given speed is inversely proportional to its deceleration. So this is very much like we did yesterday. We did a direct proportionality problem. That was subscript 1 over 2 equals subscript 1 over 2. It says here the distance, I'm just going to go distance, is inversely proportional to deceleration. And since D, they both start with letter D, let's go with X for distance. Let's go with Y for deceleration. I usually like to pick letters that are meaningful, but if they're going to be starting with the same letter, you know, maybe I pick some different letters. So distance is going to be X, deceleration is going to be Y. And when you see the words inversely proportional to, I'm going to make it X proportions, or an X ratio, so X1 over X2. So that's the beginning distance and ending distance. I just made a decision how I wanted to put it. I decided 1 on top, 2 on bottom. It doesn't matter what you decide, just decide something with X's. Inversely proportional to means when I write my Y's on this side, I'm going to invert the subscripts. So, subscript 1 on top, I'm going to put subscript 1 on the bottom. Subscript 2 on the bottom, subscript 2 on top. That's what an inverse proportionality is. This board is just like... Here. All right. So, first distance over second distance equals second deceleration over first deceleration. All right. And then if we take a look, it says a train traveling 30 miles per hour requires 180 feet to stop when decelerating at 0.18 Gs. What is the stopping distance at the same speed when it's decelerating at 0.15 Gs? So what seems wrong here is there's too many numbers, right? So take a look what it says. The distance necessary to stop at a given speed. At a given speed. So it's saying that we have a train traveling at 30 miles per hour. Right? That's the given speed. So every train we're talking about is going 30 miles per hour for the sake of this problem. It actually says 180 feet, that's obviously a distance, and it says decelerating at 0.18 G, so the deceleration is in G's. That's gravitational units, basically. Okay, deceleration is feet per second squared or meters per second squared, and the pull of gravity is 1 G. Negative 32 feet per second squared, negative 9.8 meters per second squared if you're interested. So 0.18 G would just be 18/100ths of that number. All right, but both are given in the same unit, that's what matters to us. So what I see is, all right, x1 equals something, x2 equals something, y1 equals something, and y2 equals something. x1 is my first distance, which is 180 feet. y1 is my first deceleration, which is 0.18 G. x2 is my second distance. What is the stopping distance at the same speed? So that's what I don't know. Unknown feet. When it's decelerating at 0.15 G. So again, inverse proportionality, create the proportion, put the subscripts where they belong. Pick out of the problem what they tell you for information and then substitute it in. Verify units match, so feet, feet for X, G's, G's for Y. So all the units work out, so now I can just put the numbers in. So 180 is my X sub 1. I do not know X sub 2. 0.15 is my Y sub 2, and 0.18 is my Y sub 1. Proportions created, now I cross multiply. 0.15 times x sub 2 equals 180 times 0.18. 180 times 0.18 is 32.4. And 32.4 equals 0.15 x sub 2, so I divide by 0.15. And so I got 32.4 divided by 0.15. That comes out to 216 feet. in simpler terms about direct and inverse proportionality, just so you have a way to quick check your work. A direct proportion, if something gets bigger, the other thing gets bigger. If something gets smaller, the other thing gets smaller. They directly relate to each other. In an inverse proportion, it's the opposite. When one goes up, the other goes down, and vice versa. So notice that if going from x or y1 to y2, y1, y2 got smaller, right? x1 to x2 got bigger. Right? So you should anticipate when you're doing this problem, if you're doing inverse proportion, looking for something, and you see what happens to the one thing, hey, that got smaller, you should expect this to get bigger. If it does, you probably did it right. If it doesn't, you probably got things upside down. All right, with direct proportion, it's the other way around. If this goes up, that goes up. If this goes down, that goes down. So no, that's going to be happening every time with these things. So if you have the word inverse or direct, you know at least the relationship that should be there. You don't know the exact numbers, but if it's doing the right thing, if it's supposed to go up and it goes up, you probably did it right. If it's supposed to go down and it went down, you probably did it right. So if it's supposed to go up and it went down, you probably did it wrong. So you can fix your work and hopefully figure out your own mistakes and become better for it.